talk will be by Will Rochard, and is in room.
Okay, so hello everyone. My name is Will Horsch, and I'm a postdoc in the Leiden Observatory in the Netherlands. And before I start, I want to thank the organizing committee of this Division B for inviting me to talk about examples of astroanalysis tools, in particular the ENIGMA fitting tool. And I also want to thank my collaborators in this work. So I want to start with this beautiful picture collected by the James Webb Space Telescope using two instruments, the MEDI and the NISPEC. And we heard from the Klaus Pontoppidan discourse on Wednesday that most of this comes from the PAG mission. But also there is a lot of star formation process happening in this cloud. And because of this, it's very important to understand the physics and the chemistry in these clouds. Well, if you zoom in a little bit in this cloud, we can represent this small part of this region by this cartoon. And in the low extinction region of this cloud, atoms can stick on the surface of dust grains, and because the temperature is very low, they can react in the surface and lead to the formation of some molecules in the ices. So for example, water, CO2, ammonia, and methane. But if you go a little bit deeper, carbon monoxide can also be formed, and the successive hydrogenation of carbon monoxide can lead to the formation of methanol, that's known as complex organic molecule in astrochemistry. If you add a little bit more ingredients to this scenario, for example, cosmic rays or UV processing, this can also lead to the formation of more complex organic molecules. So now that we know that these molecules can be formed in ices, the big question is how abundant they are in these star-forming regions. Well, to answer these questions, decades of ISO observations have been performed, and I want to start with this ISO observation of a high-mass protostar, W33A, and we see different absorption bands in this spectrum, which are associated with ices, except by the two silicate bands. And we have identified several molecules in these ices that are represented by the white colors, and the red ones are the molecules or ions that has not been securely identified yet. Going a little bit further now with Spitzer, we see this combination of the Spitzer observation, starting at 5.5 microns, and also combined with the ground-based telescope, VLT. We see that we may have some ices as well in the low-mass protostars that's represented by this SVS45. And one of the things that we learned from the Spitzer observations is that we do have ammonia and methanol in these objects, and we could quantify them. But the point is, from these two observations, we did not securely identify complex organic molecules. And this is one of the goals to do with the James Webb Space Telescope. On top of that, we see that if you compare the laboratory experiments in color, in this case of Spitzer observations with the Spitzer observation itself, we cannot really account for all the absorption that we see around 6 and 6.8 microns. So we should have something else that's not only water and methanol in this region. Well, talking about JWST, I just want to highlight this work that has been accepted 2 weeks ago, where we measured the infrared spectrum of methyl cyanide in different chemical conditions and temperatures. And here we are comparing with the observations. And we do see that perhaps methyl cyanide could be one of the potential carriers of these absorption bands. And this, we have a bright future ahead because we all hear that James Webb exceeds all the expectations for all the instruments. So we are very optimistic for the detection of these cones in the near future. Well, however, it's not easy to identify these complex organic molecules, and in the next minute, I just want to review very quickly the methodologies used so far. So for example, you can combine laboratory data and try to fit the observations. However, this method has not been so successful so far. as we see in this example here. So it's obvious, but it's difficult to handle by hand, because if you increase the number of components, it gets difficult to fit, and also it comes with very high degeneracy. The second method has been very successful, but it also has some limitations. So, for example, only in this range of the spectrum, you can subtract off the water absorption band, and the leftover you can fit with 5 empirical components. And we have learned a lot with this method. So, for example, this black one is associated with refractory material in the ice, and it's quite prominent if you look for the high mass protostars, but it's very weak if you look for the low mass protostars. It's not shown in this plot, but if you also compare with background stars, this feature is not even present. So must be something related to the refractory material, but this method does not really identify the chemical composition of the components, and is also limited to this only part of the spectrum. So I would say that for the JWST era, it would be interesting to invest a little bit more time on method 1. And here is where ENIGMA fitting tool comes into play. So the ENIGMA stands for the decomposition of infrared ice features using genetic modeling algorithms. And ENIGMA has 3 pillars, and I think this fits very well with the theme of this division B. For example, genetic algorithm optimization, that's a very robust method for fitting. And this fits well with the part of technology of this division B. We also have a large laboratory database, which fits well with the part of facilities, and also a robust statistical analysis, which fits well with the data science part. In a nutshell, ENIGMA gives you information about the spectral decomposition. So here I'm showing an example of a paper in preparation of a protoplanetary disk, where we combine different laboratory data, and for this we can fit well the observations. Another step is that ENIGMA can give you information about the icy column density of the molecules, and once the solution is found, then ENIGMA can perform a statistical analysis, like for example the recurrency plot, and see how frequent is one specific component, how this is important for the fit, and finally you can evaluate how well constrained is the icy column density using the histogram analysis. Just to give you a more in-depth example, I just want to talk about ENIIGMA2022. That's a class 1 protostar in the Ophiuchus molecular cloud. It's very bright and is located in a distance of around 120 or 30 parsec. But just for information, there is more information, more data coming from this region here, and I am the PI of a James Webb proposal to observe 6 protostars where we have evidences of external heating because the presence of B-type stars around this region. So stay tuned about this as well. So spectral decomposition of ENIIGMA2022. So this is the result that we got. So in black we have the observation, and in green is the model. And the first thing that I want to mention is that if you look for the band at 3 microns and 6 microns, we do fit these 2 bands simultaneously, what was not possible before. And also judging for these residuals, we see that we have a good fit, except by some parts that I want to highlight here. So this small part here, around 3 microns, we do not fit well. And there are some reasons that we explain in the paper, for example. One of the possible reasons is that this excess of extinction that we see could be also related to the presence of large grains, and we do not account for this effect yet in the ENIGMA fit tool. Could be something else, and related to the salts in ions, in ices, and there is a paper to be submitted soon about this as well. Another potential contribution would be for this hydrogenated amorphous carbon. That was one of the suggestions of the referee of the paper, and we do see that this could be a potential solution for this excess. But let's wait a little bit more, because actually ENIGMA performs a fit between 2.5 and 20 microns, and then you can also see the presence of possible contributions in the other range of the spectrum. So, not working. Yes, thank you. So now moving for this range about 6 micron. We also compare it here with this hydrogenated amorphous carbon, and from this region we may conclude that perhaps this is not present because we do not see these strong features. So we may exclude the presence of hydrogenated amorphous carbons because of this. But we have a good fit of the observations using not only water, as it was used before, but also some data that was processed by UV or cosmic ray. And this leads to the good fit that you see also in this range. And moving now for the band around 9 microns, we do see these two strong components around 9 micron, that's ammonia, and 9.8 microns, that's methanol. But not only this, we also have this purple component that's associated with ethanol in ices. And this, I want to highlight again, that's a fit between 2.5 and 20 microns, not only one small part of the spectrum. So perhaps because of this, we do have a good detection of ethanol in ices. And another thing, another step that you can perform is this recurrence plot. And here we can, for example, see how frequent is one of the components in the fit. And if you look for the first one, this component is present in all tentative solutions found by the code. So this means that this component is really necessary for the fit. But this number decreases if you go a little bit deeper, and then you just get to the point we may have some degeneracy. And I want just to mention about these 8 to 11 components that are not used for the best fit, but it means that one of these components could replace one of the previous components, and the fit is still inside the 3 sigma confidence interval. And the reason for that is because 3 sigma for 2 components fit is not the same of the 3 sigma for 7 components fit. We have a little bit more freedom, and then it's because one of these other components could be also a potential solution. We also calculated the column densities toward the layers 29, and we compare it with the observations, with previous papers in the literature. And for example, we do see for the global minimum solution that we still very close to what was proposed before. And also we can perform median analysis using the histograms and see how well constrained is the solution. And if you look, for example, for the water, we see that we don't have much variation of the histogram, which means that water is very well constrained. But if you go for the ethanol, for example, we do have more variation, and this is because of the effect of all the potential components to this band. If you want to use ENIGMA, you can find more information in the Read the Docs, so you can go for the online documentation there. You can also download the code from GitHub. That's also a possibility. And if you don't want to download the code, but just try it, you can also run directly from the cloud using this link. And this is actually a product of a workshop I gave recently for the MIRI-GTO ProtoStars programs in Leiden. But the files are available for everyone. So my take-home message is that ENIGMA provides a global fit of the infrared broadband range of protostars. A variety of experimental data is crucial for ENIGMA, and for this I also want to invite you for my talk tomorrow about the Leiden ICE database. It was already mentioned today by Professor Cornelia, but I'll give a little bit more details. And also, ENIGMA fits simultaneously the bands at 3 and 6 micron features that has not been possible before. Ethanol is possibly detected toward this source, and ENIGMA is also an open source tool, so if you want to use it, or even give suggestions and comments, they are very welcome. And last but not least, I just want to acknowledge the financial support of the Leiden Observatory, the advanced grant by Professor Vina van de Soek, and also IAU for giving me the grant, and also the invitation to be here. Thank you very much.
Thank you, Wim. Are there any questions in the room? Yes, please.
I will. Well, we've met before, and you know that I'm always talking about past. But I am interested. I found that very interesting, and I hope to be able to use this, perhaps to look at the ice part in my spectra. But you showed that excess in the infrared. Mm-hmm. I may have missed it, but I mean, I see that you don't have perhaps some pi emission from the 3.3 feature. I mean, I know there's not the other pass, so I don't know if that's why you're eliminating that possibility, but it seems to be around that wavelength?
Yes, we do have some features, but when they are present, perhaps they are seeing absorption in this range, and we have a strong feature around 3.4 microns. That's one of the characteristics of paths. So because of this, some paths has been tentatively detected here, but people did not find a good fit with the observations. So because this feature is quite narrow compared to this broad range, perhaps it's not associated to the pi emission. Could be one of the reasons.
So there is a comment from Cornelia.
Yes, thank you. Thank you, Will, for this very nice talk. I would like to ask you, just in this spectrum, you have excluded the presence of hydrogenated amorphous carbon. But what about amorphous carbon without hydrogen? Because I think amorphous carbon without hydrogen could explain a little bit the excess you might see here. What is the argument against this?
Yes. So the amorphous carbon, we do not see strong absorption features, right? Basically, we have some smooth profile, so without any strong absorption feature. And indeed, we do use amorphous carbon when we are doing simulations. So if you are doing a radiative transfer simulation of these protostars, we have to include at least 15% of amorphous carbons in the dust in order to account for the infrared excess or infrared absorption that we see in the continuum. But for this band in particular, this could not be associated with amorphous carbon because the effect of amorphous carbon should be before that range, around 2.5 or a little bit lower than that. So, and also is not associated with this strong component. But as I said, if you move for the presence of large grains or even salts in these ices, this could be one of the possible solutions that has been thought of before.
Okay. Okay, then thank you.
So maybe we can continue outside because there is another session starting at 3:15, I think. So that's the last question. So thank you very much, and thank you to all speakers this afternoon for being with us, because it must be late for you. And thank you very much.